Hello everybody, welcome to my next video. And in this one, we're gonna go on pause on the ST32 peripheral tutorials and gonna continue on the video I did a while ago where I introduced you to my DIY audio DAC project. So in that video I talked about the IC that I chose, which is this one, the 24-bit 192 kHz ADC from Texas Instruments, or DAC, and all the reasons why I chose it and how I'm gonna configure it. And now I have the prototype soldered on my board and on my board, and also the ST32 library written up to a certain point so I can show you actually working. So before we do anything, I just wanna play something that is connected to the external sound card and that you can see that it's working. And I'm also gonna enable this code so you can hear. So according to this code, the DAC is muting at a period on 1 second. So this is what we're gonna be working on today. So the first things first, I want to show you the hardware, how I soldered it, how I approached it, and then we're gonna go to the software and the library that I wrote and how I approached that as well. So this is gonna be a long video, so I'm gonna thoroughly explain what I did so you can be inspired to do something similar or the same regarding hardware and software, or how to approach general prototyping. So let's go. So one thing that I want to start with is the schematic. So the schematic is the same as the included sample schematic from Texas Instruments in the same datasheet. So this is what we talked about in the previous video. So these are the IV converters over here that convert the differential current over here to differential voltage. And because most audio players and even good amplifiers use single-ended signals, so signals that are respective to ground, we're gonna use the differential to single-ended converter over here. So we have to use 3 op-amps for each channel. So this is left channel, and you just copy this again for the right channel. So this is for configuration for a maximum of 2 volt RMS signal on output with a plus-minus 16 volt supply with a drop frequency of 217 kHz. So this is the low pass filter point of -3 dB, so that the 20 kHz is still unaffected. So this is what I talked about in the previous, how these amplifiers work, and now I want to show you how I soldered it on the board and how it actually works. So let's open a few images. So I want to start with the first image. So this is a picture of what I have on my board right now. You can see my discovery board over here. The finally arrived audio interface from China. So this is actually USB to digital audio interface. So it converts the USB to appropriate I2S audio interface. It also has the main clocks for the DAC operation that we talked about. And over here is the actual DAC board. So this main daughter board is the one that has all the analog circuitry on the output, and it has actual DAC on its breakout board over here. So it can be easily accessed on the standard 0.1 inch header, or in this case 0.1 inch raster of a board. And under that is a motherboard, you could call it like that. I have a few standoffs because under here there's a power supply. Similar connections, this daughter board and the motherboard are connected with these wires, so this is all the supply pins. The audio interface is connected with this pin, so this is the I2S connection. The ground is also connected like this. It's not ideal, but for testing is good enough. And these are the SPI lines. Again, I chose SPI over I2C because I like SPI better, and why not? And I have more experience with it. But as you can see later, you can choose I2C for controlling this IC as well. So let's have a look at the actual supply. Because this is a prototype for me to tinker with the DAC chip and to understand it and write a library and test it thoroughly, I don't need a glamorous fancy power supply that I will eventually design for the final product. Therefore, I want to use something that is accessible and small. For that, I turned to a DC to DC converter over here this big black block. This converts plus 5 volts to plus and minus 12 volts. It's really enough, even though the specification says 15 volts, but the 12 volts should be enough for the kind of signal we were going for. This is so I can use the USB 5 volt supply over here. So this is a 5 volt cable that comes in here, connects to this bulk capacitor and goes into this converter. Output of this converter goes to an LC filter and then to these headers over here. The 5 volts also goes to this 3.3 volt regulator that is needed for the digital part of the DAC. That also goes to this part. And also the 5 volts is needed for the analog part of the DAC chip itself, so it goes to these pins as well. So we have plus minus 15, 5, 3 and ground. So the next one is I want to show you is the actual daughter board on top, and then is the daughter board on bottom. For that I have this image editor open over here, so I can draw some lines so we can compare more easily what is actually going on. So let me pull up this page and let's have it side by side, why not? And let's try to, no? Can we do this? No? Okay. So let's go through the schematic. So this is the digital part over here. So if I have this, so is it working? Okay, so this is the digital part of the IC, and this is the analog part of the IC. Most of these pins, if we go to the pinout over here, most of these analog pins are supply and ground, and common and supply, EREF again. So only these two pins and these two pins are the signal pins. So these are differential current outputs. So these are the ones that we actually go any further with. So if you look in this scheme, there's mostly, if we go deeper, so we have decoupling, the output actual, again more decoupling, more decoupling, more decoupling. So there's mostly supply. So let's start with the signal. So let's go back to the schematic. And so the IV converter is the first one. So each input goes into the inverting input of the IV converter, and then the output goes through a resistor into the inverting and non-inverting input of the differential to single angled converter. So if you follow that over here, and let's have this in this color. So this is one of those and this is the other one. So this is this part. And then it goes into, I added a few labels so it must be easier. So these are single amplifier packages. So it's very straightforward to use them. If I just plug in one datasheet for an amplifier I'm looking at. So amplifiers can come in single amplifier packages or dual amplifier packages. So it's the same package, same pinout or similar pinout, but it can have one amplifier or two physical amplifiers inside. And there are two reasons why I would prefer single amplifier. The one is that very good amplifiers tend to come in only single amplifier per packages. And although this one is a very good amplifier, it also comes in two. The second reason is that, if we elaborate on the first reason, why is that? You can have a nice path of input only on one side and the output on the other. So the path of your circuit can go nicely like this. Whereas with two amplifiers per package, the input and the output is on the same page. So you have to have input over here and output on the same side, so the circuit building can be more difficult or less. But in the physical prototyping by hand, as in my circuit that I have opened right now, I tend to find it very easier to just use single amplifier packages, because it's easier to actually route and solder everything by hand, if not making your own PCB, which I'll be making in the future. The second reason, that is actually more factual, is that if you have multiple amplifiers in a single package, that same package is gonna heat up more because there's always gonna be some wasted power. So this is very easy to check. You have to go down in the datasheet, and there's somewhere is gonna be the power supply section and the quiescent current. So this is the current that's gonna be drawn by the amplifier regardless of its operation. So when the power is applied, it's gonna draw this current for its normal operation. And make sure it's per amplifier. So in this case it's 2.2 milliamps per amplifier. So let's do a quick calculation. If we have 0, so 2.2 milliamps multiplied by, so supply voltage is plus minus 15 volts, so this means 30 volts across the rails of the amplifier, so multiplied by 30 is 66 milliwatts of heat, which is not really much, but again this is just quiescent. But now to calculate the actual waste for a dual one, so this is the dual package amplifier, you can see for the SOIC package, for the 8-pin SOIC package, which is the same package that I'll be using, is the thermal resistance. So you have to choose the proper one. We don't have any heatsinks on this because these are just bare chips. So you have to look for the ambient junction to ambient thermal resistance. So this is the resistance, effective resistance from the junction, which is the actual die of the op-amp, and the ambient, which is the surrounding. So this one is the actually pretty much always the largest number. So this is for how much degrees Celsius, in this case, the temperature will rise above the ambient depending on how much internal power is being lost or generated in this case. So if we multiply the power loss in this amplifier, so remember this is per amplifier, so we have to actually multiply it by 2. So we get 132 milliwatts wasted in a 2 amplifier package. And now we multiply this with a 134 and we get 17.7 degrees Celsius. So this is how much it will heat up above the room temperature. And maybe it's summer, or maybe your case is not very well ventilated and the surrounding ambient temperature might be 50 degrees. And this will result in a 76 degree temperature of the IC. And the bigger the temperature, the faster it will deteriorate and performance will go down. And maybe you have a certain op-amp that has a larger quiescent current, therefore it will waste much more power and maybe it will be very, very hot. Therefore, when you have only one amplifier per case, you can see that the thermal resistance is the same, but now you only have one that's wasting power, therefore the total heat increase or the temperature increase of the package will be smaller. So that's more of a logical and more way of explaining why we should use a single amplifier package instead of dual. And that's basically it. But if you have a dual amplifier package, so the one that has 2 amplifiers in it, you can guarantee that these two will be much more similar than 2 of these ICs bought separate, because these two were generated at the same time, at the same temperature, in the same foundry at the same time. Therefore, these 2 amplifiers should be more similar than 2 ICs like separate ICs. That should result in a more consistent performance characteristics. So when we're talking about the IV converter, for example, which includes 2 same configurations, therefore it would be actually maybe better if these 2 were integrated on the same package. But you have the trade-off of the power loss in the same package, so it will be heating up much more. Therefore you should be maybe looking for the packages that have a thermal pad in the bottom, so it can dissipate that heat further. So it's up to you, it's positives and negatives in both cases. So this is about the op-amps. So let's go back to our thing. So now we said the signal comes into the inverting pins. Then it should go from inverting over here over the resistor, and there is the output. So it goes something like this and something like this over here. So this is the minus, plus, and output. So again, this is the single amplifier package. If you go to the bottom board, I also laid out with the same colors, so it might be easier to track. So this is the signal, so this is where the signal comes in. So it comes in into the inverting and goes over to the output. And here you might not see it, but under this capacitor, which is this one, the 2.2 nanofarad capacitor, is a resistor, this 750 ohm resistors. And again over here, so the signal goes over here, over here. So now we're here, so we have traversed to this part of the circuit. So this is why I like SMD very much for prototyping, because this SMD, in this case 0603, but also 0805 would be good, are just large enough so they go like this. so you can bridge different solder points on this standard 0.1 inch header board, and you can just connect them like this and have a little circuit connecting them together. So that's why I really like them. Plus they're not the smallest package, so they're quite easy to work with tweezers. Also they are small again, so this is fine, because if you think about all these components being a through hole components, this would waste a lot and lots of space. And by being so small, all the parasitics, inductance and resistance in lead sizes and stuff like that, it goes very, very low. So this prototype can perform very well even without a ground plane. So this is just my opinion. So now we're here. So next we need to go into the differential stage. So effectively we need to, so this is like a macroscopic scale. The output over here needs to go here, and this output needs to go over here, and we have the single-ended output over here. Of course, in between there's a series resistor, this R3, and there should be one going from the minus terminal to the output and the plus terminal to the ground. So there should be one to the ground over here and the one going like this. So let's see it on the image. So in this purplish dots, this is this amplifier. So we can see that the output over here goes over this jumper wire to this pin over here, which is not connected to the amplifier directly, because it firstly has to go through this resistor before going to one of its pins. So in this case, this is this amplifier we're firstly connecting. It goes firstly over this 560 ohms resistor over here before connecting to the plus terminal, and then it's another 270 ohms capacitor or resistor to ground. So this long lead is in this case ground because it goes everywhere. So this is this. Also you can see there's a capacitor on the bottom of these two resistors, and this is this 2.7 nanofarad capacitor over here. And in this case there's also one on the bottom of this resistor. Also you might have seen, maybe let's go to the bottom one, that I used, it doesn't seem very good, but I used two parallel resistors because I didn't have a 270 ohms one, so I used the double the size of the 270, which is 540, and I just put them in parallel and I got the same result. Also this resistor 270 that going over here is also double. So if you look the other one, so this is the other one, so this is this amplifier, so this is its output going again with the jumper wire over here, and it goes firstly through a resistor before going to the inverting terminal of this one, and then it's going over a 270 ohms to its output. So this is this path over here, so it's going this way to the output. The output again goes through a 100 ohm resistor, which is just a protection against any short circuits. Again, this is a prototype, so anything can go wrong. So to avoid any damaged components and going back to the shop, I just put a resistor, which is on the top layer over here, and then it goes through a cable to the 3.5mm audio jack. And it's exactly the same for this side over here. So if we go back to the top layer, you can't see it, but in here there's a small 0603 resistor that goes over here, and then at the bottom it goes to this connector. Also it goes also on this line, so this line can be approached via oscilloscope probe, so it can be easy to probe the output directly. Again, you could also use the differential signals over here on the output and have differential output, which is much more preferred because it's much better, because it's less prone to noise. Because when you do this differential to single-ended, as we discussed in previous video, we reduce the common mode noise. So if we have a spike on the positive input and the negative, and this minus this is 0, therefore the common mode, so the common mode noise, so the noise that is present on the both lines, will be cancelled out. I will also probably include these images in the GitHub, where all the code and these images will be available, so you can look it up yourself as well, so you won't have to keep going back to this video. So now I see 20 minutes, so this is the hardware actually done. So this is everything. Also the second channel is copy of this, so it's exactly the same. One thing again, the digital portion over here doesn't have really much. It has only the SPI and the I2S over here, and a few pull-ups and supply pins. Also, as you can see, there are a few resistors, and there are 100 ohm resistors connecting the actual wires that are going to the microcontroller and the pin. This is just so if I happen to short these wires when I'm testing and they're just flying around, they don't short anything important and fry the IC, because it is an expensive IC going from 12 to 14 euros, so it's not really the safe way to do it. So therefore I just used some 100 ohm series resistors to terminate the inputs. Okay, so this is hardware taken care of. So let me take you to my code and show you what kind of library I wrote and how I did it. So here's the main code, and right now it's running. So let's put it on stop so it won't be bothering us. So this is just a simple code. It's a part of my bigger project. So this is my actual project code. So you can see there's RTOS. So I have a crude small scale manual RTOS that we also learned in school, but we won't be using that. All that you need to see, this is the init function for this DAC. And also I have a timer over here. Since I've used RTOS for this project as well, I can't be using SysTick. So I'm using another timer, in this case timer 5, for delays and timeouts, as we're gonna see later. So all that I'm doing is what I demonstrated in the beginning, that I'm toggling mute for this IC every second. So I'm turning mute on and off, therefore muting and unmuting the outputs. And this is by using this function over here. And let's go into the appropriate library files to show you how everything works. So let's go to the beginning. Okay, so the first thing is that how I approach this library, how to write it, because I've never done something as elaborate like that. So therefore I went to the standard peripheral library of ST, because it's one of the lower level libraries that just work. And because this project has to show also my knowledge of microcontrollers, I decided to not use HAL, but low level, which is a library that I will talk about in a future video. But all that you need to know right now, that low level is basically standard peripheral library, just packaged in a new way, and it's supported in much more processor, because standard peripheral doesn't support the new L series and MP1s and stuff like that. Therefore L can be now used. So to get a hand of this, go to your project manager, advanced setting, and you can see that for all the drivers you can select low level or HAL. By default they will all be HAL, but you can choose LL or low level. So for USART, RCC timer, SPI and GPIO I used low level. Therefore it can be much more crude to use, but for this project it will be just perfect. So the first thing that I did is go to, let's say, GPIO, because I'm the most familiar with, and see how the GPIO does it. So how you can see, there's an init function, a master init function. There's an init structure that holds all the initialized settings. We initialize clocks, set certain pins, and then we apply our settings to this structure. So what we want, in this case, which pins, what is its mode, the speed, the push-pull type, pull resistors, and then we have a function that applies the settings that are stored in this structure. And then in the end, if we would have some kind of SPI or UART, we would have a command or a start function that will start that peripheral, but in case of GPIO you don't need to start it. So I went a little bit deeper. Okay, so how is this init function defined? So okay, it's a bit elaborate. So as you can see, that init structure basically has all the different settings for this peripheral. So the pin, mode, speed, output type, pull, the modes, all these are separate bytes. In this case 32-bit variables. So every setting has its own variable. So this is one thing that we have to remember. So we can implement every setting as its own variable inside the init structure. Okay, when going back, how can we apply this structure then? Okay, so basically what this does is checks a bunch of things, which pin is selected, blah 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 blah, and then every function, so every function and every setting that we just looked at, so pin, mode, speed, output type, pull, alternate, is therefore applied with its own function. So setPin function, pin output type function, pool function, AF function, and mode function. So I thought that was a master big function that does everything automatically on its own, but no, it's much more simpler. That the load is divided into multiple lower functions. So the functions there simply do one thing. It set the appropriate GPIO pin, its speed in this case. Okay, so we need functions that apply each setting separately. Cool, so this is it. Oh, and we missed this one. This is the GPIOD in this case for the LEDs. What is this one? So GPIOD is basically a pointer to a structure called GPIO type def. And it's pointing to a base. So this base is, no, it's not going right now. So this is basically address in the microcontroller where these settings are stored. And in this case of the microcontroller, the order in which these settings are stored in this structure is the same as the order of the settings in the microcontroller memory, which is not the case in our DAC. Let me show you what I mean. Let's go a little bit up to where this GPIO type def is defined. So I believe it's somewhere over here. We have to search for G. This is S, R, and GPIO type def. Okay. So as we can see, these are all the settings or the register, pardon. These are all the register for this particular peripheral. So these are all the register, not settings. As you can see over here, the settings, or actually over here, there's a 1, 2, 3, 4, 5 settings, but there are actually much more registers. So there are more registers. There's the mode register, okay, the speed, output type, pull resistors, and alternate function. So those are those settings. But there are additional registers like output data, input data, BSRR, and LRCAR. So there's much more. So this is actually holding all the registers that actually set the behavior of this peripheral. So we have to separate the functions or the settings for the peripheral and the actual registers that hold that information. So those are two separate things but kind of connected. In this case, the GPIO-D in this case is pointing as a structure to a certain point in memory. And these registers in the memory are 32-bit and are in the memory right after one another. So there's mode register, and after that is right the output type register, and after that one is the output speed register and stuff like that. But in our case, we won't have the registers one after the other. We have multiple settings in the same register. So if we go here, and let's full scale this, let's go to the register map, we can see that in the same register, so let's say register 18 has 1, 2, 3, 4, and 5 settings in the same registers. So we can do it like that. Also, we cannot have a pointer to a certain memory location because these settings are in IC that is separate from a microcontroller. Therefore, we cannot do it like that. So I wondered, well, let's do it halfway like that and then include something else. So now that we see how the low level or the standard library does it, let's see how I implemented it. So the first thing is, I just wanted, if I'm gonna use it or not, a few macros for the register addresses. So it starts at 16 and it goes 16, 17, 18, basically increments by 1. Then I implemented the type def of status, so I could have some kind of statuses. Maybe I will expand this in the future, but right now it's just fine because I'm not really using it. And here's the first thing. Here's the structure, the PCM type def. So you can compare it to the GPIO type def. So this is gonna hold all the register information and more, as we can see with the GPIO. So it has all the register settings. So these are the settings that we will be able to apply, but there's much more. There's the output data and input data registers and the control registers, and therefore I also have something more. So we have registers that will have the settings, but we can also have, in particular, these two registers. We will see these are read only, so they behave like the input data and output data register. They're not really settings, they're actual workings of the ADC or DAC in our case. Also there's the status and connection, so there's much more than just register. So this is holding all the information of the DAC state right now, so holding all the information about how it's configured, what is its state, maybe is it playing music or not. You can have multiple things like that. So this is just the core definition that we're gonna use all over, like the GPIO-X in this case, so like using GPIO-D and over here and GPIO-A. So we're gonna use this in the same way as in this case GPIO-D or SPI1 or timer1 is used all over the code. So this is what we're gonna use and to refer to it all the time. So this is gonna have to be accessible and stored in a static memory, so it's gonna be available all the time. So the next one structure is the long structure that we talked about over here. So these are the actual settings. So this is not the state of the machine. So this is just gonna be the settings that are gonna be applied in the initialization procedure. So as you can see, it's very long. So these are all the settings that can be changed. I just left the ID and ZFGX, they're read-only, so I noted that to myself, but all other settings can be changed. Also, you have to know which can be changed according to the other. So if you're gonna change these two, for example, will only take effect if this one is changed and stuff like that. So you still have to read the reference, in this case datasheet. But I commented as well as I could, so it could look similar to this library. So when you read this library, you're not totally confused and you can get around without switching back and forth with the datasheet. So this is basically all the settings that are gonna be in the initialization function. So if we go to the GPIO, so these are these settings. So we're gonna be looking for this. Then we're gonna need the init functions. And before we find the init function, we have to define also the function that are gonna apply the separate settings. So the next thing, well, I have a little bit of the settings, or I have the notes how to apply these settings, and we just blazed through this. So let's imagine you didn't see that. So these are gonna be the functions that are gonna write particular settings. So there's no universal function for writing settings, but there are going to be particular function for writing settings, and I'm going to show you why that is. So if you go back to these functions, so let's go to init and let's go for, let's say, set pin pool. So this is going to set the pin pool. As you can see, this function is very short and it's defined in .h file instead of .c. That's because it's also defined as a static inline. It's of course void, it's not going to return anything, it's just going to do its job. But it's defined as a static inline. If we go to the definition, it's static inline. So what static inline means, for static, it's going to be only available in that H file and to the C file that the H file is included with. Therefore, only available locally. And inline, which means that this function will well, inline actually tells the compiler, please try to include this function as a part of the whole operation, so the operation time and the memory can be much lower, so the usage and the execution time can be increased. Therefore, it's not gonna treat this as a function, but it's gonna try to take the insights of this function alongside with the arguments and try to cram it in the actual code that is calling this function. So this is basically an optimization. So it wants to work faster, and because ST did it, and because it seems logical enough, I implement it the same way as well. So static inline in the header file. So the C file will only store functions that will be also available to other functions. So some kind of init function, start, stop function, maybe some kind of mute functions that I showed you before. So this is a kind of function that I want other functions to be able to use. But this one, like the atconfig, this is really going to be used only by the functions in this particular .h and .c files. So it's going to be local, so that's no problem having them as static inline. And I'm going to show you where these functions are used. So the first thing is how these functions are configured. There are two parts. One is the part that's actually writing into the type def, so this is the one that's gonna actually store all the settings. So this is the one that's keeping, so this is the variable or the structure that is keep track of the state of this DAC. So this is gonna keep track of it. Therefore, every time we make a change, we can just send a new setting over SPI to the DAC, but we have to firstly store it in here so we have track of what's going on. And that's for a good reason, because multiple settings use the same register again. So in this case, for the, let's go for something more fun, for FMT. So this is the one that controls the actual data sample, so how the data is going in. So the left or right alignment, the I2S or the PCM mode and stuff like that. So this is this one, FMT over here. Let's go up. So this is the FMT. And how should we approach to applying settings that do not have the whole register for itself? So in this case, FMT only has 3 bits in the register 18 available. It starts at bit 4 and it ends at bit 6. How should we go about to applying these settings? Let's say we want to have these settings as 1, 0, 1. Let's say this is a setting we want to apply. If you just wrote 1, 0, 1, of course 0, 0, 0, 0, 1, 0, 1, 0, into the register 18, we would just drive over all the other settings. Let's say this was 1, and this was 1, and let's say this was 1. If we just applied the configuration for these 3 bits, we would just erase all the other configuration over here, or actually force it to 0, which is something we might not want. Therefore, we need to apply this setting and preserve the other bits, or in other words, we only have permission to write in these 3 bits and do not want to affect these 3. So how do we do that? Well, because I don't want to write everything from scratch, because this is why we have libraries, I use the modifier rag, which is the same one that is used by ST. So let's go to this one, let's say, and it's using modifier rag or write rag or clear rag. So let's find it where it's defined. So for the simplers, the write rag is simply gonna write what is the input to the appropriate register. So if this is the thing that we don't want in this case, because we just want to change these bits and leave this and this one unaffected. So we don't want to write rag, and we want the modify rag. And we need much more input. So we want the actual register where we want to write it into, a clear mask and a set mask. So set mask is the actual data that we want to write into that register that only has ones where we want to change the state. So it will only have numbers of 1 on these 3 bits. Whereas the clear mask is gonna have the ones where the setting is apparent. So if I can explain this, so the mask in the terminology means that where these bits do exist. So the mask for this register, the FMT register, would be 0, 0, 0, 0, 1, 1, 1, 0. So this is the maximum value in quotes of this register. The mask for DMF register would be 0, 0, 1, 1, 0, 0, 0, 0. Mask for this one would be all zeros, and this one would be all. So this is maximum value of a certain setting. And why do we use mask? Because if we use mask, we can use the mask over here with end, which is gonna say that only where this mask is 1, you can change the value of the bits that are defined in here. If this mask, for the sake of argument, let's have it over here, was 1, 0, 1, 1, and our set mask was 1, 1, 1, 1, okay? We could only set this 3, and let's say our register was 0, 0, 0, 0, so it was clear. If we use this function on this register with this clear mask and this set mask, the resulting register value would be 1, 0, 1, 1, because with clear mask we said that we can only write on these bits where it's 1 over here. Therefore, it doesn't matter if this bit is 1. We gave it only permission to do it over here and here. I hope I explained that correctly in my own words, but basically, so this is the way we can write into certain bits without affecting the others. So if you go back to our functions, so this is what we're doing here. We're writing only the appropriate bit, so we need a mask and we need the appropriate setting, writing into appropriate register. And what are those settings? Well, those are the one we skipped before. So those are here, and this whole order of things that we just discussed is described over here. So let's go for FMT as we know it. So FMT is selecting different audio formats. So it's also commented on the right, so you know for every setting what it does. So the first thing is the position. Position tells where this setting starts, on which bit. In this case 4, as we can see that the FMT starts on bit 4. Therefore its position is 4. Then we need its mask, because we see that it's very useful. So this is where these bits are all 1. And in this case mask is 7. As we can see, 1, 1, 1 is in binary 7. So this is the maximum value of this register. And where this mask is, the actual mask has to be in regard to the whole register. So it's 1, 1, 1, but there are 4 ones before, 4 zeros, before that. Therefore, we need to take this 1, 1, 1 and shift it. So if they were starting over here, you have to shift it by 1, 2, 3, 4. So you have to shift it by 4 places. So this is the actual position to the left. Therefore, the mask is 0x07 left shifted by the position where it starts. So this is how we create a mask. And the rest is very simple. So the first settings, we can go into this datasheet and let's go for the ATL. We can see that the first setting is just 0, 0, 0, therefore it's just 0, 0, 0. The next one is 1, so it's 1, but it's on the position bit. And the next one is 2, but it's here, so we have to all left shift them. No? So we have to all left shift them by 1 place. So the 0, 0, 1 is not just over here, so it's not 0, 0, 1, but it's 0, 0, 0, 0, 1 over here. So that's why we use the left shift and the position. So the position mainly used only over here, and the mask and the settings are used at the bottom over here in these functions. So this is where we actually use the mask. And this is actually what you use when you use GPIO. So when, let's say, GPIOD, and this is because it's a pointer, you have to use the arrow. So let's say you want to change the mode register equals to, let's see if GPIO moder. So it's these are the macros that are predefined. So there's an alternate, analog, input, and output. So these are the macros. So if we go to this macro where it's defined, it's exactly the same. It has these values defined, it just doesn't have the mask. But if you were to see the other settings, maybe over here, let's go to the GPIO. So this is the other GPIO settings. So let's go to the bottom, can, DMA, external, F, and GPIO. So you can see it's the same. So I said I copied what they were doing. So we set the position of this register. We firstly create its mask. So this is the maximum. So 3 is 1, 1. Therefore, this configuration has 2 bits. And these are the different configuration for this one. So it's 1 for left shifted by the position and 2 left shifted by the position. And again with the new setting. And again with the new setting over here. So this is how I approach the macros. So macros are pre-compiling, therefore they don't actually use any space on the processor because they're just copy and pasting by the compiler, and they're just dropped in place over here. Now the last thing I didn't mention is what is this if statement. So this is one additional thing that the standard peripheral or the low-level library doesn't have, is another parameter. I called it write, because these registers do not live on the processor but on a DAC that is separate from the processor. You have to write it at some point. Well, I use this write with an if statement and only write the value of this register again. If you change this setting, this is only a part of register. So it's not smart to always, when you change as just a small setting, to just again write the whole register. Therefore, sometimes when we're doing initialization, it's gonna be bulk settings. So we're gonna configure multiple settings that are all in the same register, and only when we configure all of them, then it's logical to send the setting, not after each change. So therefore I included this right, because sometimes we're gonna be using this function to configure the our handler, and then right after that send the new settings. Again, let's say if you wanted the mute function, let's find the mute over here. No, it's much higher. Okay, so when we're gonna mute the IC, the mute function will call this function and then pass it 1, because hey, changed it to mute and send the new setting right away. So it's gonna mute the IC right away, so you don't have to call this function manually. Therefore it's done by the function, because I wanted it to be as universal as possible. I hope that makes sense. And in light of that, let's go to the setup that we talked about. So the setup, again, like the GPIO init function, come on, calls different functions that set the different parameters. We have a struct init function again that initializes a certain struct according to the device. So again, it's gonna call this function that we just saw before, and it's gonna write new settings. So it's gonna write the new FMT, DFT mute settings, but it's not gonna immediately write them, because as you can see, register 18 has 3 settings, register 19 has whopping 6 settings, and this one also has 6 settings. So it would be just inefficient to just write the register after every small change in the same register. Let us just change all the settings, and then in the end we write all the new register settings to the DAC. So it only writes over here, so it's not just wasting cycles, because this would be a lot more writing than just writing the whole register after all the initialization is done. So what this function again do, they write the new setting in the handler, and then in this case they don't write, but they could also write into the register directly. As you can see, nothing in the register 22 and 23, because registers 22 and 23 are only readable because they have the ID and the flags. So we now talked about the initialization, and now let's go to the actual .c file that has the useful function that we are gonna be using. So this is the actual quote-unquote user functions. So the first we have the handler over here. So this is the one that's actually gonna have all the settings. So it's configured globally in this file. And if it wants to be included in the other files, let's say main, in the main I have it as extern. So it knows that this struct in this case has been defined somewhere before. So it's gonna use that one if we're gonna use it in other functions. Also the main has included my PCM1792.h, therefore we can do that. So let's start with the init we just talked about. So this init is like this init. So this is this function. So it firstly configures some clocks, takes some housekeeping before it applies settings, and then applies them with this function again. So the first thing that I do is enable the SPI, and then I don't have this implemented yet, but the first thing is that I check if the PCM is alive. I do this by reading the ID, because SPI, as I'm gonna show you in a minute, the SPI also has some timeouts that I implemented myself. It can return certain errors, so we try to read ID, and if it fails for some reason, disable SPI and return from this function, and don't continue with the initialization because there was obviously an error. In this case, you could process this error. You can have different errors, so this could be SPI error, and this could be data error, and so you can, when you're debugging, you know which kind of error. So it's a connection problem, it's a IC problem, or is something else. So we read the ID, and then we check it if it's any good. So if it, in the moment I'm just checking it if it's either 0 or 1. So this means that the whole transmission that we got back, so this whole return, so the information that we got back was 0 or 1, which means that no information was sent, so the line is floating or connected maybe to ground or supply. So this is a case for an error. Therefore, it again disables the SPI and returns an error. Hey, something was wrong with the SPI. I could also check for a particular part number, but as I read in here, this ID can change on different batches of this IC. So I didn't want to force a particular check for a particular number of ID, but I might do in the future. And then if we came to this point, well, it was obviously a successful connection. So we set this connection part of the structure to on. Now, we firstly set the DAC to stop, so it's gonna enable mute, so it's gonna go into mute, and it's also gonna disable its output. So if you go to the stop function, it's gonna use the mute conf and the op conf, and it's gonna enable mute and disable it. And also you can see here I'm using ones instead of zeros over here. So if we were here, we use zeros because we didn't want these functions to directly write into the device, but over here we wanted to apply this setting into our structure and immediately send this setting to the device. Therefore, this device, when it will receive this mute confirmation, will immediately go into mute. We don't have to call the send function ourselves, so this function does it for us. So it's gonna mute it and disable its operation. So this is before we do actual anything. We want to have device in a disabled state of work so we don't break anything by accident. Then we proceed by initializing our init structure. So this is a structure that's gonna hold all our initialized setting, and here we have a large list, so this is similar to this part. And we're gonna apply all the settings. So these are the default setting along with mute and operation disabled and other settings. These are all basically default settings except mute and operation disabled. So these are all default settings that are also described over here. But I'm just for the safety, and maybe you want for default settings to be something different than what the IC has for its default, you can just apply them over here. So you just change the, let's say, ATS, control space, and change the appropriate ATS. So these are the default settings and are applied with the struct init function that we defined in our .h file. So these devices are applied and in the end are sent to the PCM device. So the settings are written, and then when the settings are written, then we can start the device. So the start is basically the opposite of stop. It's gonna change the status to on and then send an operation enable and mute disable. So it's gonna disable the mute and device will start speaking. Therefore, when we step by step execute this function, you can hear that over here the music will stop and here the music will resume. And if all is well, return success. I could also point out that its start function could also have problems. Let's say that the SPI just disconnected on this point, which means that this write register function, which actually does return the error status, could return an error, and therefore this function could return an error. But by the time when we start using this function, we assume that the SPI was initialized with no problem because we just got to this point of initialization. And because when we go into the main, now back to the main, we can see that this init function, when it's called over here, but if it returns anything but success, it's gonna stuck in this while loop. For the prototyping now it's appropriate, but for your maybe project, you have this init function, and if it returns anything but success, you know that you shouldn't be using now any SPI code for talking to this DAC, because obviously something went wrong in the initialization, therefore it is unusable, so it should be looked after. So this is the init function over here. So in this case, infinite while loop, but before that just enable LED, so I know that there's a problem. And here we just toggle mute, so we can hear the actual effect of this library. So now let's upload this code. So I'm gonna upload this code. So it's gonna recompile. Oh, I made some settings, so it's gonna save all the settings, recompile, and let's enable our default view. So it's gonna enable all our view, and let's just unzoom. Oh, there was an error. I probably made a typo somewhere. Oh, I probably made a typo over here when I was talking. what is the error? Oh, yeah, of course, it should be device. So device is the actual pointer that's coming in, but before it was the PCM, which is the actual variable, which is a global variable. So if you were using this one, you should be using it like that. But I'm using the actual argument in this case because, well, I want to be universal. So where is it? Over here. It's device. But you can do it either way. So this should now be working. Okay, let's unzoom. Okay, and let's upload code right now. So it's compiling and it's going up. Okay, so now let's run to here, Control R. So let's go F5 into the function, let's half step it, and I'm gonna start playing this music, and hopefully it will be long enough so we'll hear. So you can hear that no music is playing right now. And let's go back to our function and let's enable SPI. Okay, we read the ID and let's see the device structure, what it wrote. So you can see it wrote something. So ID was 31, so it's a success. Now it's gonna check. Well, it's more than 0 and less than 11111. Therefore it's gonna go and it's gonna update it to on. So connection is on. It's gonna stop it. As you can see, it wrote this to registers. And then it's gonna initialize this struct. And if we go to the end of the initialization of the struct, we can see that the new values that these were applied into the struct. Now let's go into struct init function, and we're gonna see this light up. It's gonna configure it with new functions. Yes, so these are the new settings that are gonna be applied, but most of these are also default 0. Therefore, they're not gonna be nothing special. But over here, these functions are gonna apply these settings into our DAC. So if we just F7 return to here, this function has now been sent to the DAC. And now if we click start, you can hear that the music is playing. And let's go with the music. So this didn't happen because the initialization was successful. We're gonna enable this timer. And I'm gonna just use F8. So this executed the mute control. So it just sent the mute control. And let's talk about this function again. So the mute control is basically a global extension of this function, because we said these functions are only available to these C and H files over here. Therefore, I need a bigger function, so to say, that actually uses this function, but it's for an added bonus because it actually uses just a simple interface. So which device, and in this case our handler, and mute, 0 for unmute or 1 for mute. So it uses this logic to translate it to these macros. Therefore you don't even need to use these macros, you just need to use the 1 and 0. And same can be applied for different settings, maybe the operation enable, maybe information type. So maybe you want to change the input data type, so maybe from 24-bit to 20 or 16-bit, so you can use that function. Let's find it. So you can use some other function that changes and calls this function, and by using 1 for write, it can send those changes immediately, just like I use it over here. So it changes the enable. So if we go over here into this one, let's put a breakpoint over here. Okay, so we are now inside this function, and now in this case the mute parameter is 0, so we want to unmute it, so it's gonna go over here. And what is this gonna do? You can see this value is 81, so this is the mute bit, which is the first one, and after this function this is gonna clear to 0, and the IC will receive the unmute value. Therefore it should be playing music. So this is how it works. So this is quite a long video, the longest I had until now. Oh, and the music stopped playing, that's why it wasn't working. Now it should be working, yeah. So this was the longest video, but I wanted to give a comprehensive look into how I wrote the library. So it's not just an introduction to this DAC, so how you can make this DAC, but it's also how can you approach to it. So a few ideas how you can approach to writing libraries and maybe integrating your ICs that you want to use in your project, not just using the raw code and just sending it some bits that you will not remember a few days later what it meant. So again, I'm gonna include these two PCM files in the GitHub, and also these two SPI files, so you can read them yourself. So what I'm basically doing is just writing to these registers. If you watched my SPI video, you know that for reading, the most significant bit of the address must be 1, and basically it's more glamorous because low-level library doesn't handle errors and waits for the empty registers, therefore you have to do it by yourself. So I just here wait until the transmit register is empty before I can fill it with new transmit data. And while I'm doing the waiting, I'm also checking if there's a 10 millisecond timeout present. If there's a timeout, I return an error and stop the SPI communication. And this is the same for the receiving data. So for reading data, you're also waiting for the transmitted register and for receive. So it just doesn't wait for infinity. So it has a certain limit. So this is where the timeout or the timer that I initialized in the main, and it's over here. So this delay millisecond function exists with the timer initialized over here. But I'm also gonna put this in a separate function. But you can read it and study this function on your own. I just explained the main PCM function, and this is the one that we're gonna be actually using. So thank you for watching, and I'll see you in the next video when this probably be connected together. But before that, we're gonna probably look at the low-level library at more detail. So again, thank you for watching, and I'll see you next time. Bye.